All right. So I was asked you problem C on this one, and C is a beautiful problem. So we need to get this. So I'm gonna actually approach this a couple different ways. Um, the first thing that leaps out at me is, look, this resistor here is in parallel with this resistor here. Agreed? So this capacitor here. And this capacitor eventually is going to shut down this loop when it gets to 12 volts. How do I know that? Because that's what it's approaching 12, getting closer and closer. So that means that this thing here is going to have a 12 volt drop. Okay. If it has a 12 volt drop, I can calculate the current for it, could I not? And so therefore I could go V equals IR. The V is going to be a 12 volts drop across there equals I times 15,000 kilo ohms. And so I would get 12 divided by 15, 1, 2, 3, and I get 8 times 10 to the negative 4th amps. Negative 4 amps. Knowing that nothing is going through that capacitor when it shuts down the circuit, all of it has to be going through this resistor here. I also know I need an 8 volt drop. How do I know I need an 8 volt drop? Because this is 12 volts. I got to lose 20 volts if I go this way or I go this way. This way I've got 12 volts, so there must be 8 volts here, right? Dropped across there. So I'm going to go V equals IR. I get 8 equals 8 times 10 to the negative 4th times R, and I get that R has to be R has to be 8 divided by the answer to the previous one. So it's going to give me 10,000 ohms. So that's the first way I would think about doing that problem. Or 10 kilo ohms. Second way to do this problem is to look at it and go, well, when I first shut down the circuit, when I first shut that thing down, and maybe this is, let's go the other way. Another way to look at it is I've got a loop, right? Okay, I've got my old Kirchhoff loop right here, right? So if I go up here, I got a Kirchhoff loop right here. This loop right here, I have to lose all my voltage. And so I might do something along the lines of, well, 0 equals negative 20 minus, I'm basically doing the same problem twice, just packaging it differently. Let's do it anyways. Okay, so when the thing shuts down, I've got minus I times R2 minus the same I, right? Because it's got to be the same current going through that one when the whole thing shuts down, when that capacitor's at full power. It has to shut down that one. R1, which is, by the way, 15,000 ohms. So look at that. I got two unknowns, so I can't quite solve for that. So I go and do my other Kirchhoff loop. My other Kirchhoff loop would be 0, make the bigger loop. The bigger loop would be, so this would be positive 20, up 20, minus IR2, minus, now how much volts are you going to drop across here? Well, I know, just looking at my pretty picture, I'm going to drop 20 volts across there. I could also, by the way, solve for the charge, right? Okay, you solve the charge. But in the previous problem, it asked you to solve for the voltage anyways, right? Okay, so since it solves for voltage anyways, we know that we're going to, sorry, this should be 12 volts, minus 12 volts. So that means if I lose 20 volts going through total, and 12 of them are here, then I must lose 8 going through IR2, right? Because this is 12, 8. Okay. Once I have that, I can replace that in here, and it goes 0 equals 20 minus 8, replacing it here, right? Minus I times 15,000. Once I do that, I get negative 12 equals negative I times 15,000. That gives me my 8 times 10 to the negative 4th amps. Once I have that, then I can go ahead and proceed down this road. Okay? So that's two ways to look at the same problem. It's kind of important. This is an important problem because I think it's a good problem. This thing's fair, okay, and legit in that sense. And I hope this makes sense. If it doesn't make sense, let's zoom this because this idea is big. Okay? All right, stopping.